So the talk is going to be today about what the group is doing at Baylor University in this area. We're going to try to answer a couple of questions. What is adversarial robustness? General perspective intro for those who are not super familiar with this. And then we'll talk about how adversarial robustness relates to fairness. And how can we evaluate adversarial sensitivity at all? And then we'll talk about how can we produce trustworthy AI. Just as a quick recap of those of you who are not in Texas, Baylor is an R1 university. We're celebrating that we just got into the next level of research there. And we also got into the top 10 most trusted universities in the country, in the US. And that is important because this talk is about trustworthy AI. So we kind of need we're pushing this as well in the university. We have new research capabilities, and we do all this work with grad students. 2 of them are right here in the back. And we are growing our lab, and this is the people we have, except for the 2 on the bottom right. That's my dog and my cat. Those were the founders of the lab, and then we expanded with actual people can get things done. And half of these are Latinos. We're very proud of the diversity of the group. We have students from Peru and Cuba. We have also others from Thailand, Bangladesh, and India. All right, let's talk about adversarial robustness. I'm sure you've seen this picture before, or something that looks like this. And the whole point of the adversarial problem set, or the setting of the problem, is that there is some type of noise that if you add it to some type of input, image, text, sound, whatever it is, it can change the prediction of a model. I'm old enough to tell you that back in the day before adversarial learning, we used to just add noise. Many of you are old enough as well. We call it salt and pepper noise, or random noise, or very particular types of noise. This type of noise, or perturbation as it's called, it is not just random, but it looks random, but it's a targeted noise, which is an improvement on what we used to do back in the day. This is not an idea that is relatively new. It's been around for a little bit, and the credit goes to the people listed here, have done tremendous work. And the whole point of adversarial models is just to find the best perturbation, not probably because you want to exploit it for bad, hopefully, but because you want to fix your models. That should be the main focus. And the examples in computer vision for this are the greatest, because they have, oh no. Hold on, I'm gonna close this. Well, the picture you see there, it is a turtle that has a pattern in the shell. And it is probably obvious to you that it's a turtle, but for a model based on DressNet and BGG, specifically BG16, it is detected as a rifle, or it completely ignores the fact that it's a turtle, which is also important. It completely disregards the fact this is a turtle. But the more alarming fact is you can change the class. So it's a targeted attack, and you can have these type of attacks commonly. Why do you care about this? Why should we care? Because the military is investing in this, not only industry, but the military. So the military is thinking that others are doing it, so we must also do it to protect ourselves. So things can get dangerous pretty quickly if we don't pay attention to this. So there are some advice to prevent your models from being attacked. And so I'm going to list them. I did not come up with this. These are well-known facts out there. Number 1, thou shalt not train on data you don't fully trust, because of data poisoning. Number 2, thou shalt not let anyone use your model or observe its outputs unless you completely trust them. because of model stealing or black box attacks, which are pretty common. Number 3, thou shalt not fully trust the predictions of your model. That's kind of a non-obvious one, but it's because of adversarial examples, precisely. So the problem setting is adversarial data sources are then need to be found through an optimization problem that looks like this. We're trying to have a loss function, generic one, take whatever model it is, a transformer or some type of classification model of your choice that has input X, and you're trying to find a perturbation delta that belongs to, X belongs to class Y, and the model parameters are theta. So you're trying to find this delta within this region or this budget that you have on delta. The main idea in vision, computer vision, for example, is that if you add this noise that is not perceptible to a human being, so it is small enough but to change the classification, but it's small enough that you can't see it, it's not obvious to you. And so it is a min-max game in which you're trying to find an adversarial example, which is the inner maximization term, that is trying to cause the greatest loss. While on the other hand, the minimization is that you're trying to use this information to retrain your model adversarially so that you minimize that maximum loss that you could ever have. And so it's a beautiful optimization problem, very challenging, and the current state of the art says that the most successful solutions to this is using different types of optimization. There are 3 groups of research in adversarial learning. One of them is kind of focusing on tackling the problem from a local search perspective, which is a lower bound on the objective. And it's trying to do, it's relatively easy to do with current computing power and the common knowledge we have in the state of the art. The second group is combinatorial optimization. This is something that will solve your problem exactly, but it has a very difficult, you have a lot of challenges analyzing and proposing the actual optimization problem you're trying to solve. And there's the third option, the convex relaxation, which is an upper bound objective. So it's not an optimal solution or an exact solution, but it's a relaxation that will enable you to relax these constraints and find a solution that is quasi-optimal. So the warning that we always give here is that the problem, if it's not obvious, is that you have these loss functions that look very terrible. If you're an optimization person, this is a nightmare loss surface. And so over parametric models today are trying to tell us also that you can, the more parameters you have, this can look a little bit smoother, but still finding then adversarial examples on those, it can be challenging for that reason. The solutions that we currently know are PGD, projected gradient descent. And the idea is that if you have a perturbation delta, it's a region, and you have this loss function, you can think of it as a ball, your perturbation ball, and you can calculate the gradient, and the gradient on that loss function for that perturbation can take you out of this region, and PGD will project you back into the periphery of your solution space. So this is nice in theory, but Ian came up with a nicer way of doing it. Ian Goodfellow, you remember this guy, my dear friend Ian Goodfellow there, who wanted to take a selfie? I'm kidding, he doesn't know I exist, but we took a selfie on a NeurIPS in 2018. He's the author of a deep learning book, which is a segue to my book. If you have a friend that needs a deep learning book, this is for beginners. We all have that friend who wants to learn machine learning. This is the gift for the person. And the nice thing is all proceeds go to LatinX and AI. All right. So what Ian said was the fast gradient sign method was just looking at the sign of the gradient and project back to the periphery, but this has an effect of usually projecting back on these corners. You can find more about this online, of course, but this is pretty simple to do, and it is certainly successful. So that's it with the intro of the state of the art on adversarial learning. So let's talk about robustness and fairness. What does one thing have to do with the other? First of all, I think we all care about fairness. We're here in a group of Latinos, and we know sometimes firsthand experience what unfairness may look like in some scenarios. But in the case of machine learning, you can think of this as things that will cause different type of changes in accuracy or performance of models. So with the student Korn Suksa, who's sitting in the back there, did some work on looking at different factors of what fairness looks like. There are plenty of fairness measures out there. Plenty of them. We're not gonna claim we cover them all, but the ones selected here cover some of the most important ones, and the others are dependent on some of these. So I think we do a great coverage here. First one is looking at accuracy as an unfairness measure. The idea is that if you have a model that you train to be robust, using adversarial robustness or adversarial examples, the new model then has different accuracies for very specific classes. And if that class or label is a protected class, then you might be in trouble. So this can lead to class-wise accuracy and fairness. In the case in the screen, this can be, for example, a change in the deer class. After you train robust with adversarial robustness, you're making actually better the deer class. But if you look at the dog class or the cat class, the classification accuracy drops in these cases, and we all love cats. So this is trouble. So there's a second metric that we can also define as robustness and fairness. This is related in a way to the previous one, but we can show that the amount of the epsilon, which is related to this perturbation delta region, can vary in size, or you may need a larger perturbation to cause a successful attack on some classes. So if you can see, this is obviously a disparity in some classes like cats again, and horses. For horses, we may need a larger perturbation to cause a successful attack, while attacking cats is super easy. So there are classes that are more vulnerable. And so this metric will show that once you train your model to be robust, then you're causing some kind of unfairness here. We also did a study on the success rate on these attacks prior and after robustness, and prior to being trained for adversarial robustness with different epsilons. And the story is the same. You can see disparity between certain classes. Cats and horses is the obvious example here in CFAR 10. But we can take this to other data sets, as we'll show in a minute. Here in this one, we're just trying to show that the adult data set, there's a problem. This data set has different salaries and different demographic information about people, adults, and then there is a question here that we ask if groups of adults who earn less than $50,000 a year or greater than $50,000, how does that affect the classification or the unfairness after you train robustly or not? In terms of the data set size first, which is what we're showing here, and then in terms of money. So we're looking at differences that are very common on the lower end of the spectrum, and then on the higher end, it's little difference. So there's also another issue there. Another measure of unfairness is leave one out unfairness. This is, if you've done machine learning research long enough, you know about leave one out cross validations. It's a similar concept. You're training your model, but leave one out in your data set. But in this case, we're interested in looking at which data point in this data set, if I take it out, it's going to cause the most significant change in the performance of the model or the confidence on classification. And so when we can find these samples, we take them out, we can quantify which classes are more weak, or which labels are more weak. And so we need to quantify that and make sure that these are acceptable or not to us, so that you can fix or protect or add more data as you need. So what we're showing here is in the table is that the average model on the first LUF, it is having a change in certainty of up to 79. And the number of samples that we can take out before the whole thing breaks down is 29 out of 110,000. 2,900 out of 10,000. Finally, if it is not obvious that training adversarially causes unfairness, we have this one that is called equalized odds unfairness. This is another measure of fairness. The idea here is that you will have a given classifier F, and then you're trying to find the maximum difference between the expected values of confidence in your classifiers. And here we come to the income. So we have D0, it's a classifier that it's trained only with the lower end of income, and another one, D1, that is on higher end. The whole point here is that there's a disparity of on the equalized odds from when you train it adversarially robust and when you don't. So as you train it to be more robust against adversarial attacks, you're causing a lot of, or it leads to unequal odds. And so we did a study also in what this means for specific races of people, and the problem is still the same. So then, is there a way then to quantify robustness so that we can, or quantify the weakness of this model so that we can then address problems in the first place? So yes, we can. There's an easy way, that is that you train adversarially and then using the whole data, find all your gradients, and then go to bed and come back in 2 years and find your solution. Or you can use one of our easier models that come up with in the lab. Shout out to Korn as well. He came up with this idea of using the Jacobian matrix of a subset of the data, and then it will determine, or it can help you quantify how sensitive is your model to specific adversarial perturbations. It's very easy to show this in computer vision. If you're interested in looking at this from an NLP point of view, come up to our poster later today. We have also adversarial examples on NLP. But in computer vision, you can then, for example, quantify whether a fraction or a part or a region of your input image is more sensitive to attacks than another. And so in this example, we're showing that if you take the upper portion, I think you can see it better on the second, on the third, number 4 on the screen. That in the lower portion there, you can see perturbations there. You can, right? But not in the previous one, or it's a little more, it's a little harder to see. That's because the first part is not so sensitive in comparison to the second part. So it requires a lot more effort to actually perturb the input and cause an adversarial attack, a successful adversarial attack. And so you can then look into this by drawing maps pixel by pixel to analyze which regions of your image or your classifier actually are more sensitive. And if these are dense networks, for example, at the input layer, you can directly do something about that neuron that is very sensitive to an attack, or that neuron in combination with the others in the group or in the sequence of layers, which is also another work that we're doing in our lab. We're looking at how sensitive, how adversarial perturbations move across layers, and how we can adapt some of those or limit the effect of adversarial perturbations, so that you can, if you already have a trained model, you don't have to retrain it adversarially to fix the problem, but you can just, for example, modify some activation functions there. And if you want to know more about that, talk to my student Corin and I. We'll be happy to talk about that. Here's another example with CFAR 10. In this case, the most susceptible part of the adversarial text is in the bottom half of the car, or well, in the image, really, in the classifier, that in comparison to the lower part. In general, we can say that our models are this way of quantifying adversarial sensitivity. It's in accordance to doing this at a full scale, and it will save you quite a bit of time. So then the big question is, so now if we know what an adversarial attack is, and we know that adversarial robustness leads to unfairness, and we know now how to quantify sensitivity, and if our model is sensitive, then how do we fix it? Well, that's a big question, because we're trying to address this from a trustworthy AI perspective. That is people need to trust on these models, and it's a big deal. You know, trust is very expensive. So people from industry here will agree with this. If once a person or a customer base loses faith on a product because of a problem, then it's very difficult to bring it back or to regain the trust. It's expensive. So we better get this right from the beginning. We've been proposing to have a two-step approach, and a third one using quantum machine learning. But the idea is to then involve classic optimization or classic numerical optimization methods, and introducing very specific objective functions. For example, in the first step, we're trying to encode the different measures of fairness as constraints on optimization problems. That is challenging in the sense that not all fairness measures translate directly into very nice constraints that hopefully are even have a feasible solution, but some of them can be. So we need to find this, and once we find it, or the ones that your stakeholders care about, you can propose them as constraints on an optimization problem. And now, depending on those constraints and your objective, you can then decide whether it's a convex optimization problem, in which case you are so lucky, and then you can resolve this very optimally using quadratic programming or linear programming or your choice of optimization approach. But in general, let's say that it's not convex, then you need to try other options or alternatives. And this requires a lot of again, I agree with the people who say knowing numerical optimization, it's a great skill to have in machine learning right now, especially in adversarial machine learning, because then you can look at these constraints, make them to be equality constraints or inequalities, and what does that matter? And can you make the whole thing convex by using some tricks? Or if not, then what's the best we can do about this? So in the worst case scenario, you can even try something like genetic algorithms for optimization, or unconstrained optimization even, or evolution strategies. Those are things that work, may not be as effective with respect to time, but they will get things done eventually, no guarantees. However, you can still use some tricks to implement this in GPUs or CPU and do parallelism here. So once you have defined this constraint from the literature and based on what you care about, the next step, it's sort of understanding the trade-off between fairness and robustness. Now, the part I like about this work that we're trying to do here at Baylor is that we're trying to impose budgets or propose an optimization problem that will allow you to put a budget on fairness and robustness. So if you care more about fairness for some particular model, then you can increase your budget here for that particular fairness aspect. Or if you care more about robustness than in fairness because of the nature of your model that is not affecting people in any way, then you can lower your budget on that piece of the general optimization problem. So you can satisfy both fairness constraints and robustness constraints at the same time. Now, the problem with all of this is, of course, that this is going to be a huge optimization problem. Now it comes down to having a model that may have several bounds that you can study and spend time trying to understand what it means and how these bounds change your optimization search space or your feasible space. But once you find these optimal things, I think the result has great implications on multimodal approaches. I put this figure here because the analogy is clip in the sense that you can switch there your CNN and your LSTM by a big vision transformer or some other transformer for text. So you have the multimodality there, and train using your choice of training method. And so the last thing we want to do, and this is what I say, it's a bet that I'm not sure it's gonna work, but if it does, this is gonna pay off over time, I think. So quantum machine learning is the nature of some of these fairness metrics allows you to propose them as a quantum problem in which you can evaluate some of these fairness metrics in a quantum space. So if this pays off, you can then put that in a quantum circuit, on a variational circuit, and evaluate very quickly some of these fairness metrics. So that is something that I want to put out there for people interested in quantum machine learning. But I haven't met other people that are interested in quantum machine learning. Anybody? Just me and my student? All right, cool. That's what I thought. So please contact us. Corin, raise your hand. That's my student, Corin. He and I are doing adversarial machine learning, robustness, and fairness. So if you have any questions about that, talk to us and come check out our poster today. Thank you.
So my question is mainly in the terms of, right now you explain how to be kind of defensive in terms of a specific perturbation. But what happens when the perturbation is not one, but a series of multiple perturbations? How will kind of the model or this kind of robustness can be prepared to multiple attacks instead of just specific ones?
That's a great question. So I think the approach that we're considering there is to add the different perturbations as different type of constraints in the general optimization problem. So you may have a specific constraint or objective and constraint that is associated with a particular kind of attack that you have. So you have multiple kinds of attacks that you want to be robust against. You will need to increase your problem size and by adding more constraints and add something to the objective function as well. That's a great question. It will grow the problem really. I mean, the solution is out, but it's going to affect the size of the problem itself, definitely.
Hi, thank you for the talk. Very interesting. I'm curious about what do you think about the sort of the fact that in this problem, attackers sort of have the same amount of resources as defenders, let's say. So cryptography, for instance, sort of protects us because there's this information asymmetry where the protector has this piece of information that an attacker, no matter how hard they try, they're not going to break it. With robust machine learning, it's not quite like that, right? They both have the same access to the same set of computational resources. Do you see this as a problem where you create a defense, the attacker creates an attack, you create another defense, the attacker creates an attack, and sort of, do you see it in a way just going to keep going ad infinitum, or what is your position on trying to understand this?
That's a great question. I believe I'm an optimistic. So I thought cryptography before, and I know that I have to teach it as how the students to be paranoid. But I'm an optimist. However, I agree exactly what you said, that you have to make the assumption that an attacker will have the same resources. However, I think that there's an opportunity to get adversarial robustness. Well, one of the beauties of adversarial robustness poses an optimization problem that is approaching a unique solution, is that regardless of, well, not regardless, but if you know the attacks specifically, some of these constraints that you would put in place and how you formulate your objective function can lead to protect your model against any known or unknown attack that is based on perturbing input in specific ways. So as long as you know what kind of specific ways those are, you can make some guarantees. That's the beauty of doing this with numerical optimization. So you can give some guarantees that your model will be robust against with this budget, for example, or if you go with the previous step with no budgets, then you can make some guarantees that there will be no known attack that you can throw in today, as long as it is based on this type of general umbrella of attacks. But I agree that not knowing if there's a new type of attack that we have not conceived today, then we're in the losing game for sure. We will need to keep coming to NeurIPS and find more about these new adversarial attacks. Thank you for the question.
Hi, so along those lines, and I'm sure a lot of us are going to go check out the poster from your student, but can you comment at a high level how the use of quantum technologies might also address the issue that you were just discussing? Right, because that guarantees that if somebody messes with the input, you're going to be able to detect it from a high level understanding of, quantum.
Well, from a quantum perspective, I think there's a lot of options. So my other student, raise your hand, Bikram. He's my quantum guy. So the way I see it, I think this is very personal. It's a very risky business to be in quantum right now. But I think there's an opportunity to propose some operations as a variational circuit that will allow you to conceive multiple unforeseen connections between or how input is mixed by entangling qubits of information. The limit, however, is that number of qubits we have right now operationally is 5. Really, you can use 4 if you use IBM, but so everything we have is simulation. But if we can conceive a very large input and we can entangle some of this inputs, we can, using quantum, we can conceive some unknown types of mixing or entangling or mixing information as you go through a variational circuit that will enable you to maybe conceive more robust systems. That is pure conjecture, but that's how I think it's an opportunity there. Thank you for the question.
With that, thank you, Pablo, and maybe another round of applause, please.